Hey guys, this is Carrie, and in this video we're going to be revisiting our number guessing game with the intention of creating a program where the computer can guess our number instead. So let's look back at our old game here. So in our old game, the computer thinks of a random number from 1 to 1,000. And we're gonna try to guess the number in as few moves as possible. Now, I love to do things like this because it's kind of like a game. We have to come up with the best possible strategy. Now, one strategy we might use that's going to get it correct is to just guess them in order. So, nope, that's not right. So we're trying to search for the correct number here. And I think that should make sense, right? When we type in these guesses, we're searching through for the correct number here. So these are all going to be examples of something called search algorithms. Algorithm sounds really fancy, but it's basically a search procedure. Algorithm means procedure, sorry. Algorithm means procedure. So if it's a search algorithm, this is a procedure for searching for something. So one example of searching for something is called a linear search algorithm. And this guessing method that I'm using here, where I just go in order, I think I'm up to 8, 9, 10, and I'm just guessing in order. That is a linear search algorithm. Guessing the numbers for the guessing game in order. What we mean by linear here is a variety of things, but one thing it could mean is sequential. Okay, so here we go. Some similar examples of this would be trying to find a friend's number, or not friend, a business's number in one of those old phone books, business's phone number in a phone book. By looking in order. It's going to take a really long time unless that business is like Aardvarks, where it's AA or something. But linear search is oftentimes not efficient. One example where linear search can be efficient maybe is if you think about Google search results. If you go through those search results in order from the top down, because they're sorted by value, by clicking on the earlier results, we tend to find what we want. So for a linear search, this is going to take me somewhere on the order of, because there were 1,000 possible numbers, somewhere on the order of 1,000 possible guesses, depending on where that random number is. But in the worst case, this is going to take me 1,000 guesses and not very efficient. Another strategy I could do would be, I could guess, from top down here. So 1,000, and then 999, and then 998, and then 997. And this is also going to be a linear search algorithm because it's going to take me close to 1,000 guesses, the same number of guesses same number of numbers here, to get it right. One final example of a linear search algorithm would be for me to guess random numbers here, like my favorite numbers, and then ignore the feedback from the computer, but keep a list of the numbers that I've guessed. And as long as I guess all of the numbers eventually, and I'm ignoring the feedback each time, as long as I guess all of the numbers eventually, that would also be a linear search algorithm because we're testing all of the possibilities. There's a better search algorithm that we can use for this problem where we can guess the right combination here in 10 moves or fewer. So that search algorithm is going to be called a binary search algorithm. So what a binary search algorithm is going to do is it's going to allow us to, I think it's 10 moves, going to allow us to guess the right number in 10 moves or fewer every time. And remember, the numbers range from 1 to 1,000. So before it would have taken us like 1 to 1,000 moves, this will take us between 1 and 10 moves. So the way that binary search works is rather than look at the whole range here, we're always going to guess the middle number. And that will split the possible numbers into two groups. And by means 2. So here we go. We'll split these in half, so we'll guess the middle number here, 500. We know that our number was too small, so we have to guess a higher number. So now we're going to go, the middle number between 500 and 1,000 would be 750, so this will split the range in half. Oh gosh, I didn't read the feedback. I think it said that our number was too small. Okay, I have to read the feedback this time. So our number was too small, so 750 to 1,000. What is between, I have to get a calculator out. 750 plus 1,000, oh gosh, 1,000 divided by 2, 875, so I should guess 875 next. 875 is too small, so I want to get the middle number between 875 and 1,000, so I'll average them. 875 plus 1,000 divided by 2, so I want to guess 938. I don't know how the rounding will mess this up here, but 938. Also too small, so we're going to be between 938 and 1,000. So 938 plus 1,000, the middle number would be the average 969. So we'll guess that next. That was also too small, so we're going to be in between 969 and 1,000. So 985 would be the next middle number. That's also too small. Wow, this is crazy. It's a really big number. So we're going to be between 985 and 1,000. So we'll get the average by adding those and dividing by 2. So we're going to be guessing 993. Our number's too large now. So we know our number is between 985 and 993. So we'll add those, divide by 2 to find the middle number, 989. This number is too large, so we're going to be between 983 and 989. So we'll divide that by 2, 986. So this is the middle number left now. This is too small, so we're between 986 and 989. So we'll average those, and we'll get 988. Oh, well, this is clearly not right. I think that every time I was clicking back and forth, it was doing something with the number of tries. Or maybe I forgot to reset it after guessing all of those things. This is not the right number of tries. It took us less than 10 tries, guys, I promise. I just don't want to reshoot the video. But you can see how that binary search strategy, if we ignore the punchline of that crazy number of guesses, that was an error somehow in my program, allows us to guess the right number in 10 moves or fewer because it constantly will half the range that we're looking at. And so this is a really good method for doing this. All right, let's try to design a computer program that uses a binary search algorithm in order to find the correct answer. So I'll call it guess numbers 2. And before we go on to programming this, another example of a binary search algorithm, going back to this phone book one, would be, let's say we're looking for our friend, Mr. I don't know, Mr. Lot. One strategy we could use is we could look in the middle of that phone book and we could see what the top letter is. Maybe there's a lot of L names. So we'll rip the phone book in half, throw out half the phone book because maybe we'll see that the top letter the first time looking in the middle of the phone book is L-I or something. It's Mr. Lee or something. And then we can look in each part of the phone book, looking in the middle and then throwing out half of the phone book. And that will speed up your search for Mr. Lot in the phone book. So okay, so let's take a look at programming our computer game. So in this version, we're still going to have no HTML. In this version, the computer, we think of the random number. from 1 to 1,000. So I'm going to keep track of those numbers. Let min equal 1. Let max equal 1,000. And so the computer is going to announce out to us the parameters of the game. Alert out. And let's see. The computer is going to say, think of a number from, and then it's going to plug in min to, and then plug in max there. Don't tell me. So this is an alert from the computer. So let's just get that right now to see what this looks like. It didn't work, so I'm going to go to the JavaScript here. I'm missing a parenthesis after my argument list. I forgot a plus sign here, so we need that plus. Missing parenthesis after the argument list. Thinking of a number. Let's try it one more time. Yeah, it just took a second to update. Think of a number from 1 to 1,000. Don't tell me. And it's plugging in 1 to 1,000 here, so if we change the range from 1 to 100, think of a number from 1 to 100. Don't tell me. But let's keep it at 1,000. All right, so the user thinks of the number. Now, in order to guess this number, the computer is going to guess the number in the middle every time. The computer will guess the number in the middle every time. This is a binary search algorithm, a binary search procedure, because it will split the searchable range into 2 sections each time. All right, so let's see. We're going to, in order to do this, maybe we'll set computer guess equal to, the computer's first guess is going to be between min and max here. So it's going to take the minimum number, add it to the maximum number, and then divide it by 2. Now maybe you can see what the problem is with this code. If we take 1 and we add it to 1,000 and we divide it by 2, the guess is going to be a decimal. So we're going to have to round that. So we're going to be using the math.round function in order to do that. So let's alert out the computer guess just to see if it's correct, the program so far. So think of a number from 1 to 1,000. So I'm going to think of like 666. The computer's first guess is 501. So it looks like it's guessing correct because it rounded this to 501. Now, we actually don't want the computer to take a single guess. We want the computer to guess until we say it's correct. So while our response is not equal to correct, the computer should keep guessing. So maybe what we should do each time the computer guesses is we should alert out the guess. And maybe it's not really alert. Maybe the computer is asking us a question. Prompt, my guess is, and then add in the computer guess here. Please let me know if my guess is too low, too high, or correct by typing and I'm going to use single parentheses here by typing too low. Wait, too low is like this. Too low. Too high. Or correct. And in order to store our response here, we should say, let's let our response be whichever thing we type. So I'm going to comment out the while loop for a second because I don't want to create an infinite loop. Let's just check if this part is working here. Think of the number from 1 to 1,000, don't tell me. I'm thinking of 666. The computer's guess is 501. Please let me know if my guess is too low, too high, or correct by typing one of these. So I'll say it's too low. and it looks like it runs. So what we want to do is we want to have the computer continuously do the same thing where it guesses the middle number each time through. So we're going to run this every time. Now the problem with just doing this, and I'm going to actually delete these lets because I'm not declaring new variables, I'm just going to be editing these old variables, is we need to update the minimum and maximum possible values here. So if the response is too low, then the computer is going to say, okay, well, their number was too low, so the minimum value is no longer 1 for possibilities. The minimum would be the computer's guess. And the maximum is unchanged. If our response was too high, then we want to say the max is equal to the computer guess. Because their guess was already too high, so we know it's not going to, the maximum possible value won't be any higher than that. And then finally, if they were correct, what should we do? Well, I'm running into a bit of a problem here, which is I noticed that if we put this at the end, the computer is going to, even if they get it correct, guess again. So I really want this to come before the responses. So rather than define these things out here, let's let the computer guess be some impossible number. So we'll let the computer guess start off as the minimum number -1. And we'll let their response be equal to something that's not the word correct, so just an empty string. And what this will do is it will automatically send us into this loop. So the computer's first guess is going to be wrong because it's outside of the possible range. Our response is going to be nothing. And so it will send us into the while loop. The response is not equal to correct, so then we're here. And then lastly, if the answer was correct, then what we want to do is we want to alert out the number was plus the number, so computer's guess, and it only took me tries. So we actually also need to define a tries number here. So let's let tries equal 0 to start. And then every time through, we're going to update the number of tries. So tries will equal tries plus 1. All right, I think this program should work. One thing I noticed, though, is that what if we don't give one of these responses? We should have a comment here, which is else alert out, please use the specified feedback and only reply too low, too high, or correct. Okay, so let's take a look at this now and see how fast our computers can guess it. So I'm thinking of 666. So I'll write that down here. Oh, and I think I'm going to mess up the tries if I keep going back and forth. So let me restart this. I'm thinking of 666 still. All right, so the computer's guess is 501. I'm going to say that's too low. 751, that would be the halfway point now. That's too high. 626, that's too low. 689, that's too high. Too low. Too high. Correct. The number was 666 and it only took me 7 tries. That's pretty impressive. Let's think of a new number here, and no matter what number you think of, if you do the problem right, it should take less than 10 tries. So the computer is guessing an outcome with a possible 1,000 outcomes in less than 10 tries. All right, so think of a number from 1 to 1,000. Don't tell me. This time I'm thinking of 123, but the computer doesn't know that. So I'm going to say too high, too high, too high, too low, too low, too low, too low. Correct. It only took 8 tries this time for us to get the number. All right, I think the worst case scenario for this is if I'm thinking of a number like 1,000 or 999. So let's try this with 999, and I'll reload this. All right, so my number's gonna be 999. My guess is 501, too low. And I'm just gonna copy and paste this because I think every time it's gonna be too low. Let's see how long it takes to get 999. 9 tries, pretty impressive. All right, so that's the way that this algorithm works, and it's pretty powerful. I hope that this video made sense, and I'll see you guys in class. Bye.